And we've already talked about Le Chateliers principle again. I thought about putting on the board. But remember we said that, well, I'll go ahead and do this. Does this work? If you're trying to, okay, so what is this?
Just a beaker.
Just a beaker, yep. And I'm going to go ahead and I'm going to put some liquid in it. I'm going to make that water, so let's just pretend that's water. And I'm going to dissolve, try to dissolve what is this? Sodium chloride. Yep, very good. And I'm just going to, have you ever, I bet you can picture this. I'm going to try to dissolve it so that I have, this is called a sludge. Sludge at the bottom. Okay, in other words, I have gone past this, the water is saturated, okay? So in this case, we talked about this being a dynamic situation where this solid NaCl is actually in equilibrium with NaCl AQ. What does AQ mean? Aqueous, dissolved, yep. Okay, so it would look like this. NaCl solid in equilibrium with NaCl AQ. And we talked about sometimes that's exothermic, sometimes that's endothermic. And then we talked about one way to stress the system is to change its temperature. So if this is kind of like, well, we already talked about Le Chateliers principle. Well, we did. Okay. So the Le Chateliers principle that always deals with a system that's in equilibrium, could be a chemical reaction, could be a solubility issue. And I like what this video said. It's in what, not static, but what we call dynamic equilibrium. So it's not to say that it's frozen. You definitely have things going from the left to the right, and you have things going from the right back to the left again, just like the video we saw. So Le Chateliers principle deals with stressors. One of the stressors, do I have a list down here? Oh, sorry. And one of the stressors is temperature. But one of the stressors, like we saw in the video, is changing. Remember when they added the chicks to the reactant side? Okay, more chicks over there, more gals, excuse me. In that case, if you can stress the system by adding more reactant or adding more product, not to say that I should put it this way. At that point, once you stress the system, it's out of equilibrium. Okay, not to say it won't reach a new equilibrium, or maybe the same equilibrium, same Kc. Okay, it depends on what your stressor is. Okay, so these are all different ways. These are all different ways to stress a chemical equilibrium. Okay, we talked about temperature. Okay, we talked about concentration. We're actually going to talk a little bit about changing the volume of the container. That is so fun. Next to that one, I'm just going to throw at you, in order for that one to make sense, to me, you basically have to be dealing with gases. Oops, goodness. It is so cool. If you change the volume of the container that your equilibrium is in, something's going to give. You're going to get a new equilibrium concentrations. Okay, same Kc if it's the same temperature. Speaking of Kcs, okay, so these are your Kc expression, equilibrium constant expression. Okay, so of course Qc takes the same form, but Qc is a snapshot. Qc is a reaction quotient, not necessarily at equilibrium. Okay, so let's pick on changing the concentration. Okay, just like we said, adding more gals to the left side. Okay. So let's see, so you have on your test, I'm going to ask you kind of questions like this. What if? What happens if? And the way this is worded is, what if the system is at equilibrium and then we increase the concentration of A? So first off, you're going to have to find A. A is a reactant. Okay. Well, can you see where, let's see, how do I say this? I'll do this. Basically, if you increase A, okay, you're going to put more of that. This is going to be more than it was over here. Okay? Those are equilibrium concentrations. This is your snapshot. And does this make sense that if you have more in the denominator, let's see, your QC is smaller. Yeah, your QC is smaller. And we said if your QC is too small, then you need to go to form more products. Exactly. That's exactly it. Your QC, your reaction quotient, will be too small because you increased A, which is in the denominator. And one of the things we talked about in part 2, this is part 4, we're going to come back to part 3. One of the things we talked about in part 2 was if your reaction quotient is too small, then you need to make more products, which it's going to, we say proceed to the right. Products are proceed to the right, you'll hear me talk about. I like Le Chateliers' principle instead of kind of thinking it through. What I think usually works is if there's a chemical equilibrium sign right here, okay, right where the thing is, and I am a reactant, okay, if you increase me, it's kind of like tug of war. If you increase me, instead of, I kind of push that way, okay. If you decrease me, actually I'm going to pull this way. I don't know if that's kind of, it does the same thing. So a new equilibrium will be established with new equilibrium concentrations. Not to say that your Kc is going to be the same, as long as it's the same temperature. Okay? All right. So you guys can kind of go back and forth, but what if, so it's going to favor what we say the product side. So do you buy this, that C and D are on the product side, the molar concentration of C and D will what? Increase if we increase A. So do you guys already have these, I guess, don't you? So A will be at the new equilibrium will be greater than it was at the old equilibrium. Does this make sense to you since B is another reactant? Okay, A is going to go on overdrive, converting to form C and D. Does this make sense that B is going to be less? Yeah. In your new equilibrium situation, B is going to be less, A is going to be more, and C and D are going to be more. Mathematically, you keep the same Kc. So your Kc expression, your new equilibrium concentrations have to mathematically, when the dust settles, work out to be the same Kc.
Would you have to have excess of B to make this happen?
Well, that's a good point. This is assuming that it's not limited.
Okay.
Yep, this is assuming you're not going to run out of B. Yep. Yep. Very good. So this right here says the ratio given by the equilibrium constant, that's Kc, okay, will be the same. Kc only changes when you change what? Temperature. That's right. Kc changes when you change the temperature. Yep. Okay. So here's another what if. Now this is slightly different, posing a different scenario, and I kind of mentioned a minute ago. If this is my equilibrium sign right here, I'm back to A, B goes to form C and D in equilibrium. Now if we remove some A, I already kind of told you, I kind of think of it as pulling. If we remove some A, actually it's going to favor the reactant side. But if you look at what happens is if you decrease this amount, according to your reaction quotient, that's going to make your numerator, it's going to make it bigger, right? Your QC is now going to be bigger than your Kc. And one of the things we said before, if that's the case, then you have too much product and you need to go take some of that product and convert it to reactants. Okay, you need to split those couples up. A little video we watched. Okay, so you can either kind of think of it in the tug of war thing or think through it, what happens to your reaction quotient when you start messing with the molar concentrations, and how that relates to your Kc, which is set in stone. So we could kind of ask some kind of analogous questions. So does this make sense if I am favoring the reactant side? Okay, your new equilibrium concentrations of your C and D will be less. Okay. Your A will be less, and I kind of think of this like, well, no duh, you removed some A. That was kind of the premise, right? Your A will be less. What about the molar concentration of your B? Do you already have it there?
No. Is it going to be greater?
It'll be greater. Yeah, exactly. Because it's pulling it this way. Perfect. I know it feels kind of counterintuitive, maybe, but that's really the way the dust settles. Yep, B will be greater. But again, your new equilibrium concentrations all need to follow the whole molar concentration of the products raised their stoichiometric coefficients divided by the molar concentration of the reactants raised to their stoichiometric coefficients, the Kc expression. Your new equilibrium concentrations have to add up, in a sense, to what your old Kc was. All right. So we could we could pick on the product side and think through it also. What would happen if I increase C? What happens to the molar concentration of A and B if I increase C, the new equilibrium concentrations?
Wouldn't it be less?
Be greater, because
Greater, yeah.
Yeah, it'd be greater. And again, I'm not good about thinking through the QC compared to KC, but I kind of think of it almost as a push. Yep, it would be greater. Yep. So we increase C, that makes A and B greater. We increase C, what does that do to D?
That would be less.
Makes it less. Yeah, very good. Okay. And I think I have at the end of this notes actually kind of like a little mini quiz to kind of overall kind of talk through how this all works. So we said K, or your KCs, your equilibrium constants, are for a specific equilibrium. Oh my gosh. Your KCs, we said, are for a specific balanced equilibrium. So if you change the set of stoichiometric coefficients, you get a different KC. I think that's kind of cool. They're also specific for temperature. But we've been talking about one way to stress a chemical equilibrium is to monkey with its temperature. Okay? And the direction that the equilibrium will go depends on if it's an endothermic equilibrium or an exothermic equilibrium. So you probably already see in your notes. If it's endothermic, it takes energy in, okay? It'd be a positive delta H of the reaction. And we're going to put energy over here as basically a reactant. And if you're kind of with me with regard to the whole pushing and pulling, okay, if I add heat then to an endothermic reaction, I'm actually similarly adding a reactant. Okay? Now we do definitely get a new Kc, but it's kind of like the video we just watched. Okay? So in this case, if we add more heat, does this make sense? It's a pushing sort of thing. We're actually going to form more C and D. We're going to get a new Kc though. So if we get more C and D, does this make sense at the higher temperature, for endothermic reactions anyway, at the higher temperature, will your Kc be larger or smaller?
smaller.
You're forming more C and D, and Kc is equal to molar concentration CT, CD, raise your stoichiometric
Yeah,
coefficients.
larger.
To be larger, exactly.
I was thinking it would increase the A and B, add it backwards.
No, actually it's going to decrease A and B. Yep, very good, yep. So I have a couple of slides here that look very similar, and this slide is for endothermic chemical equilibrium. So heat is considered a reactant, okay, and we get a different Kc, and our Kc is actually, we're going to have more products, which makes the Kc at the higher temperature higher. Only for endothermic equilibrium. Because guess what the next slide talks about? Exothermic equilibrium, where the heat of the reaction is negative. Yes. So if it's exothermic, then we'll put heat as a product. Yep. Exactly. So it's exothermic, we're putting heat as a product, we're over here, okay? And then I kind of challenge you to think about, pushing or pulling. If we add more heat, if we heat it up, we're going to push, okay? So now, at our new equilibrium, we'll get a new Kc, and what will we have more of? What do you think? Yep.
Yeah.
We'll have more CD. Exactly. Or sorry, AB. We'll have more AB. CD. Have more AB. Yeah, we'll have more AB. If we have more AB, okay, do you see where actually our KC is going to be smaller at the higher temperature for an exothermic equilibrium? And that's what this is. For an exothermic chemical equilibrium, the higher temperature will have a lower Kc. Lower temperature will have a higher Kc. Phew, I know. If I was gonna get ready for a test in this, I've told you before, I'm not good at memorizing things, so I don't like memorizing these inequalities because they're like switched, you know what I'm saying? I would like think through it, but that's just me. Okay? That's the way it works. New Kc values at these different temperatures. Okay. Well, remember I said this is only good for, or it has to have gases in order for this whole volume change to work. This is so cool though. I was looking at this today. I'm like, oh, that's so fun. So I'm actually going to kind of take you through a proof of what changing the volume. So again, I have in this box I have a chemical equilibrium, reactants going back and forth to form products. Okay, and I'm going to squish down the box, or I'm going to take the box and I'm going to make it larger, basically. So I'll take you through a proof. Don't worry if you're like, well, that I don't follow that proof, but maybe I bet you will. So our equilibrium constant expression looks like this. Of course, brackets mean molarity, yeah. So I'm going to kind of start there, break that out, okay? And so for each one of those molar concentrations, I can break it down into moles of that component divided by volume, moles of that component divided by volume, moles of that component divided by volume, moles of that component divided by volume. This actually kind of gets back to, remember the extra credit homework maybe some of you guys did? It seems like all of those V terms cancel, but when will they cancel? When will all of these volumes, you know, it's the same volume, when will they cancel? They all cancel. When you have the same number of moles. Yeah, when C plus D is equal to A plus B. When you have the same number of moles on either side of the reaction arrow. And they're going to cancel. But since they don't, we're going to actually have to pull out that term. We're going to kind of split it up. Mathematically, it looks like this. Like, are you serious? Of course, N are its moles. So we have moles of each of the components raised to their stoichiometric coefficient times 1 over V raised to this power. Where if you look at it, the C plus D is the coefficients for the products minus the A plus B, which is the coefficients for the reactants. By the way, that later on is going to be called, this right here is delta N, change in moles. All right. So the manipulation done from left to right there is actually to kind of clean up the inverse of volume. If you have the inverse and you have it raised to a power, you can actually take the inverse of that if you go ahead and take a negative through your exponent, and that's actually what's been done here. Okay. So now I've changed from, and I don't know what your notes look like, but now I've changed from the Kc, or equilibrium constant expression, to a Qc. Qc is a snapshot. The reason I kind of did that is because, to me, we are stressing the system, okay, when we change the volume, and you're back to, it's not an equilibrium, so Kc doesn't apply. So I kind of, that's what I thought anyway.
The notes, it still says Casey.
Yeah, but,
Change that.
well, you can put it in parentheses, because, yeah. But to me, I think we're applying the Chateliers principle. It's no longer an equilibrium, and you got to kind of look at what's going to happen. So if that exponent of volume, which now is the sum of the coefficients of the reactants minus the sum of the coefficients of the products, if that's positive, then actually we're going to have, our QC is going to be larger. Does that make sense? If it's positive, our QC now is going to be larger than our KC. I know, it's a lot of hokey dokey math stuff. Okay. So if it's positive, then we said, if your QC is larger than your KC, we said you have too many products, okay? And your products need to go split up to form their reactants again. And the other scenario is, what if that exponent of V is negative? If the exponent of V is negative, that means it has a diminishing effect on your QC. Anything raised to the negative power is like a fraction. So that means that actually your QC is going to be less than your KC. And if that's the case, then you don't have enough products. So it's going to have to proceed to form products, from reactants to products. So I've just kind of, the previous slide kind of talked you through proof to get to here. And I meant to tell you that I have a very easy way to know here in a minute. If you look at a chemical equilibrium, as long as you kind of keep your wits about you, what effect changing the volume is going to have. But this is kind of a proof as to why this works like this. Remember that that exponent up here of volume is just dealing with stoichiometric coefficients. That's all A, B, and C, and D are, stoichiometric coefficients. Like, those are nice, round, pretty numbers. Okay. So this, if you want to put a star here, this is the bottom line. This kind of summarizes how Chatelier's principle works with regard to changing the volume of a system that's in equilibrium, assuming that volume is assuming that equilibrium has gases involved in it. Okay. So increasing the volume will favor the formation of the substance that occupies more volume. All right, here's my chemical equilibrium sign. Here are my reactants, and here are my products. The one that occupies more volume is going to be where the side that has the stoichiometric coefficients, which are the largest. If you add up the stoichiometric coefficients, whatever largest, that occupies more volume. Okay? Because remember, we said the coefficients, according to, is it Avogadro's law, I think it is, the coefficients, the moles are directly related to the stoichiometric coefficients for gas. All right. So here's an example here. Now I'll give you a heads up though, and actually I have an example here in a minute. I must be talking way fast again. Oh my gosh. Okay, of course G means gas. One of the things we already talked about is if you have a chemical equilibrium and the physical phase is S, what do you do with it? Or with regard to the equilibrium constant expression? Yeah, it doesn't appear. Solids and liquids do not appear. So those appear. So which ones, the 3 moles of gas wins out, okay? And I like this trend, the slide I told you to put a star on, because it's like more volume favors more moles. What do you think, what if I shrink the volume, what side will be favored then?
The side that has the less.
The side that has less moles. So it's kind of nice, okay? So according to what we just talked about, if the volume of this equilibrium, say you got the whole hydrogen combining with oxygen to form water in equilibrium. If you increase the volume of your container, according to this, you will have more water break down into form hydrogen and oxygen gas. Now, what happens to the Kc when you change the volume? Nothing. Your Kc is constant, right? But a new equilibrium is established with new equilibrium concentrations. Cool. Yep. And this says if you, and that is the trend, but this also confirms or says if you, in this case, make the box smaller, and I don't know why volumes have to be boxes, but if you decrease the volume, it will favor the side of the equilibrium with fewer moles, which of course is the product side. I just think this is so cool to think about. So if in this equilibrium you wanted to shift it to the right, okay, you'd make the volume smaller. Right? Isn't that cool? Okay. Anyway, So in order to convince you of all of that, that last little bit about the volume affecting the new equilibrium concentrations, I'm going to take you through this proof. And it's actually kind of good to for you guys to see how this whole thing would work. So we're going to pick on the formation of ammonia from nitrogen and hydrogen like this. And what do the little E's mean?
Equilibrium.
Yeah, so these are equilibrium concentrations, okay? So the thing, I like to picture it in a box, minding its own business, and these are the equilibrium concentrations. And I can't remember, I think the first thing we're gonna do, notice the Kc isn't given. Can we get to Kc yet? So you need to be able to kind of do that. So let's write the Kc expression. It'll look like this. The stoichiometry, or the molar concentration of, in this case, the NH3 raised to the second power. Molar concentration of NH3 raised to the second power, that's the stoichiometric coefficient. Okay, we're going to plug those equilibrium concentrations in, and they look like this. Do you already have this one too?
Yes.
Okay, good. We're just knocking this out to get our Kc. Remember, when you're writing Kc expressions, don't worry about including units. And round it to 3 sig figs. This is your value of Kc, 0.0610. Now, you guys told me that the Kc is going to stay the same. Okay, so here we go. Let's just, for kicks, we're going to double the volume. We're going to double the volume. Sometimes I have to concentrate on what does this mean. We're going to double the volume. N stays the same. Okay, volume increases. So what happens to molar concentration? Does it go up or down? How many people think molar concentration would increase? How many people think molar concentration would decrease? Why would it decrease?
Because there's less moles per.
We're diluting it.
Yeah.
Yep, less moles per volume. It decreases. Yeah. So, how much does it decrease? Well, we'll get to that in a minute. All right, back to our original trend. So, in blue kind of says what my question would be. We're going to double the volume so it favors the side of the equilibrium with more moles. So it would favor the size of the reactants. So our new equilibrium concentrations will have the same Kc, okay, but it will have, when the dust settles, more reactants. So let's see if that's the case. All right, so we need to come up with the new equilibrium concentrations. If you want to put a little subscript E here, you can. You can put this E2 if you wanted to. This is our new equilibrium. Wait, no, that's not right. Oh, it's a snapshot. Sorry, it's a snapshot. It's not equilibrium. Final answer, not equilibrium. Okay. So we are going to decrease the concentration of the N2 in half. So instead of 0.921 molar, it's going to be 0.461 molar. The H2 is going to go from 0.763 molar to 0.382 molar. And the NH3 is going to go from 0.158 molar to 0.0790 molar. So let's see, what sort of subscripts would I put there? I could put maybe new, okay? So these are new, it's before a new equilibrium has been established. So how can we see if that the system's now out of equilibrium? How can we take those new concentrations? Plug them into Q and compare to K, exactly. So Q is our snapshot, our reaction quotient. So there are our new molar concentrations plugged into our QC expression, which mirrors our Kc expression, but it's not at equilibrium. So it's 0.0790 squared divided by 0.461, and also the denominator 0.382 cubed. So we're going to compare this QC, we're going to compare this QC with our Kc. 3 sig figs, I get 0.243. That's higher, isn't it? So it's higher, and based upon what we said before, if your QC is too high, you have too much product, and your product needs to go back into form reactants, which is favoring the side of the equilibrium that has more moles. So that was just kind of a proof of, you could do that with anything, changing the volume. You could decrease the volume and kind of see what your QC looks like compared to your KC. This is a good kind of look at KCs, QCs.
So if the amount of moles were like switched, and there was like 4 moles on the right and 2 moles on the left, then there would be products
Right,
would need to be converted.
exactly.
I mean, reactants instead
Mhm.
of products.
In that scenario, you told me there's 4 over here,
Yeah, instead of.
and if you increase the volume, it favors here, so more products would be formed, yeah. In this case, more reactants are formed. Yep,
Okay.
yep. And that's increasing it, but if you decrease it, the opposite. Yep. Cool. Well, do you guys have these?
Yes.
Okay, good. So this is that little quiz thing I was saying. If you want to put test, you can, because to me, this is kind of definitely one of the things I'm going to test you over, and this is kind of what the questions kind of look like sometimes. I don't know how much of it is on your test, but. So we have a chemical equilibrium, and is it endothermic or exothermic?
It's endothermic.
It is endothermic. So do we put heat as a reactant or a product? Reactant, yep. So I'm going to go ahead and put heat over here. Very good. Okay, and we asked a few questions about that. All right. Now, this is characteristic of this sort of question. It basically, for all of these stresses, I am only asking for the number of moles of NO for each one of these stresses. Because, I could ask all sorts of different, what the impact would be on different things, and I'm just only on the NO. So that actually is a product. So what happens if we add more reactant? It's kind of, you can look at it generically. Okay. What's that? How many people think it increases? Yay, very good. Awesome. Okay. What about if we add more of the other product? Adding more product.
It's gonna be less.
How many people think it'll increase? How many people think it'll decrease? Very good. It will decrease. You got it. Perfect. Very good. This is all about NO. So what will happen to NO if I remove some of the reactant? How many people think it will increase? How many people think it will decrease? Very good. Can't fool you. Perfect. And I really like tomorrow's lab because, I can give you a heads up that tomorrow's lab doesn't have any, it's not quantitative per se, it's qualitative, which means you don't really have the number thing going on, but you have kind of the visual thing and your observations. So it's kind of fun. All right. Increasing the volume of the reaction flask. Now, before you answer that, I'm going to draw your attention to, no, I guess I don't need to. They're all gases, aren't they? Seems like, oh, that's a homework. Okay. There's no solids or liquids up here, but a common mistake is if you have something that's a solid or liquid, you kind of take their stoichiometric coefficient 2 and put it as the number of moles of gases. You're like, no, that doesn't work that way. So we got 1 mole and 2 moles, right? So we're going to increase the volume, and I'm over here with the 2 moles, so I've increased the volume. How many people think that'll increase the NO? Me too. I think Quade agrees. It will increase the NO. Yeah. Very good. You got it. All right. Lowering the temperature. Oy vey. So, you know, you can kind of think through it, or you can kind of think of the tug of war. I guess this is one of the things that so you guys told me it's endothermic, so I would put heat over here. Okay. So heat's over here, and I'm gonna lower the temperature. Oh my goodness. So actually I'm gonna pull it out. I kind of picture it like that. So we're gonna get a new KC, and then you need to know which side it will favor, but can you see if I lower the temperature, I'm trying to think what my answer is. How many people think NO will increase? How many people think NO will decrease? Oh, sorry. Actually, go back. Oh, you all said increase. Let's see.
Because my thought was there'd be less heat working on
Oh, yeah, that's right. I put it over here. It's over there. Oh, yay. Okay. Yep. Okay. So I was at the wrong spot. Yeah, I was at the wrong spot. I got my side steps. So it's endothermic. You guys are right. You guys are totally right. You guys are great. Because endothermic, so I put heat over here just like I did up there. And if I lower the heat, it's going to actually favor the reactant side. And what we're asking about is a product. So it's going to decrease. You guys got it right. Good. Okay. Oh, all right. Darn it. I figured out how to make that not come up. I just need to fill up. Now this is a classic. Now do you see helium in the, no, helium is not a reactant, helium is not a product. Helium's great, it's one of the rare gases, it's an inert gas, so it's great for, it just kind of hangs out. So, I'll just ask it this way. Well, I'll put it this way. Actually, there are three choices. Increase NO, decrease NO, or NO stays the same. How many think it will increase NO? Decrease NO. NO stay the same. NO will actually stay the same.
But so would that be the same thing as decreasing the volume, right? If you added it in.
Well, according to Dalton, the gas particles behave independently, and actually chemical equilibrium is about the number of particles of the molar concentration of that particular gas. So if you put filler gas in there, it doesn't affect the other gas's ability to react or do what they're going to do.
But if you did make the volume or decrease the volume, it would decrease the mole or the.
Yeah, if you decrease the volume and physically like made a smaller container, it would favor the side with fewer moles.
That's what,
Yeah.
That's what I was.
Yeah, but just adding an inert gas doesn't change. Yeah. Nope. So let's take a look at these. These will be due on Friday, 1557. And they look like this. I actually looked at these. Okay. They're kind of fun, I think. So, chemical equilibrium, it's kind of like what we did just a minute ago. Let's see what my hints are. You know, I asked different questions, or your textbook asked different questions. So it's exothermic. We picture energy as a product. And the first one is, explain how, well, overall question in 50 at the top. It says, explain how each of these will affect the amount of H2. If I'm on a test, doing a test, I will find H2 and I'll put a question mark next to it, okay? Because it's easy. It's like, I don't know what I'm trying to find, right? So then it says, what happens if you raise the temperature of the mixture? And we've been talking about that. So just kind of answer those. I'm not going to, you guys did pretty good. Did better than I did. Let's see. Doubling the volume. Now, this was the one I told you, be careful. I have little blue circles around my gas phase things. Yeah, so which one has more, which side has more moles? Trick question. Which side has more moles of gas?
They're the same.
They're the same. Yep. Yep.
So increasing the volume and decreasing it would have no effect.
Yep, yep. It makes your delta N 0, and so your V raised to the 0th term is 1. So it has no effect. Yep. Let's see what else I have. Catalysts, we talked just a little bit about catalysts in Unit 2 when we talked about reaction mechanisms. Catalysts only make the equilibrium, in this case, come to its equilibrium concentrations faster. So it's not going to affect it, right? 58, different equilibrium, has to be endothermic, similar questions. Again, kind of, orient yourself. How would each of these affect the amount of HI? I find HI, put a question mark there. So I think you'll do fine with those. They're kind of fun. 63, we're going to increase the volume, and the question is, let's see, what effect does increasing the volume? I think for that one, 63A through C, to me, it's going to form more reactants or form more products. I think that's kind of what I'm after there. Or go to the left or go to the right, however you want to say it. For the next one, which would you expect the forward to increase with increasing temperature? So, of course, we're going to look at whether it's endothermic or exothermic. We're going to increase the heat and see, again, is it going to favor the reactant or product side? There you go. Not bad. So tomorrow, fun and games. I'll already tell you, though, for your lab write-up for this one, you're going to need to write your chemical equations, definitely. So I'm hoping my pre-lab, I've already got something so I don't have to write them out again, but you guys do.